Hello, let's look at the homeworks from graphs 10.1. So one of the problems was on making a graph, what is called the intersection graph, and they explained how it works. So I hope that I'll give this exercise that you learn how to interpret a situation and turn it into a graph. And so this was called the intersection graph. And so the first 3a, we had the sets 0, 2, 4, 6, 8. So notice that I'm going to call my node, the name of my node is the set. Okay, so the sets are nodes here. So that's the thing, or vertices. Vertices or nodes can be any type of object. They could be persons, it could be numbers, it could be sets, like here. So we had this one, we have this one. I'm not using the A1 or 2, whatever they use here. It's much clearer if I use just the description of each set. Then the next one is 1, 3, 5, 7, and 9. What else do we have? 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. And then the last one is 0819. 0819. And so how is the intersection graph works? You have an edge if the two sets have an element in common. And so one thing that you'll see is that actually graphs encode quite a lot of information, and also therefore it kind of takes a while to build the graph. So you cannot just, it's not advised to just start drawing lines at random. You should be systematic. And so how do you do this? You go from vertex to vertex and say, okay, what can I connect here? So what can I connect with this one? So in other words, which of these guys have an element in common? Not this one, not. This one has an element in common, so I have to put a vertex between them. What else? This one, an edge between them. So this one has one in common, so a vertex, an edge, and then this one also as an edge. And now we have taken care of the first set. So when we talk about putting in edges for the next one, we never have to go back to this one anymore. So we can ignore this one now if you want. So to make that kind of, do I have kind of pinkish? Yeah. So I'm reminding me I have done this. So now I'm going to look at the next set here. Let's look at this one and draw edges with the remaining ones. So there should be an edge, and if you see it, there should actually be an edge between all remaining four, right? Because this has 1 in common, this also has 1 in common, and this has 5 in common. Okay, so I'm now done with this guy too. So what else? Now, so this one. So notice that I don't look at the first one anymore. Now, as far as this is concerned, I'm not going to look at these two because I know if there needs to be an edge, it's already there. In both cases, there was one. So what about this? Well, how does it compare to this? Well, nothing in common, and here we have something in common, so we have another edge here. Okay, so also now this one is done. And then finally, I just have to think about, let's say, it doesn't matter which one I take now. This one, has it anything in common? Yeah, it has, so I put an edge between them. And this is how the intersection graph looks like. This one now, and of course, there's nothing to check anymore, so I'm done. Okay. All right, that's how this intersection graph works. I'll do the second one here. So we have the nodes here. A1 was the negative numbers, which I'm going to write as the integers with less than or equal to 0, including 0 was a part of it. A2 was the set of all integers, so I'm just going to write these integers here. A3, what was that? That was the even integers, which I can denote as 2z, if you remember still from before. So the even numbers. A4, even the A4 was the odd, so I'm going to write here odd perhaps. It is the same as 2z plus 1, but let me write odd here. And then A5, this is the multiples of 3, which we can write as 3z. Okay, and okay, so now do the same thing. We'll start with A1. Has it anything in common with Does it have an even number in there? Yes, of course it does. Does it have a multiple of 3 in there? Yes, it does. Does it have an integer there? Yes, sure, everything integer. Is there an odd integer? Yes, everything connects here. Okay, again, I'm done with this one, so go to this one. What 2z? 2z contains odd numbers. No, there's nothing between a3 and a4. Between a3 and a5, yes, there are even numbers that are also multiples of 3. For instance, 6. So 6 is a common element here, and of course this always is gonna an arrow there, right? A connection there. So an edge there. So this is gone. So let's go to the next one. Notice I'm not even doing actually in order. I'm just going through my list. Let's do this one now. Okay, I'm gonna go that one. Odd, but only the one that I've not scratched out, right? So is there anything that an odd one has in common with a5? Yes, 3 is a common element, and of course, for the same reason, we have this here. So I'm now also done with the odd ones. And then finally, is there an edge between these two guys? And there's clearly an edge between the two of them. Okay, so again, the intersection graph of this thing. And then for C, I hope I'm not going to do that anymore. Okay, let me quickly do it here. It's a lot of, these are the elements x less than 0. These are the negative elements. These are the elements between -1 and 0. So that is -1 and 0. That's this interval. I mean now an interval here. A3 was the elements between 0 and 1, the interval between 0 and 1, open interval, not including the endpoints. A4 was the open interval between -1 and 1. A5 was the open interval from everything bigger than -1, so from -1 to infinity. So therefore, let me also denote this one. How can I write this in an interval here, right? So I hope you see it. It's everything from -infinity to 0, not including 0. And then the last one was just everything, so that is from -infinity to +infinity. So I repeat, this means I mean interval. All the elements between -1 and 0. This curly thing means that there are not included endpoints. So let's start drawing intersection. Make the intersection graph. Now I'm going to start from this one because it connects to everything. That's it. That way, because everything consists at least of one real number, right? There are none of these are empty, so it's always has something in common here. So that's for that. That's the one with the most connections. Okay, let's go to the -1 infinity. So everything that goes from -1 to infinity. Yes, there is an element in here. It connects here because, for instance, 1 is in there. Here also the same for 1 is in there. From -1 to 0, yes, actually 0 is in there. I don't know why I said 1, because 0 is actually an easier element. And from -1 to 0, yes, there's another element in here, namely 0. Okay, so also that one is the one with a lot of is done. Okay, what about the interval 0, 1? So I'm taking out this guy, okay? 0, 1. Does it have anything in common with the interval from -1 to 1? Yes, there are a lot of elements in there, like a half, for instance. Not 1, because it's 1 is not in either set, right? But a half is in both sets. From -1 to 0 and from 0 to 1. No, they have nothing in common because 0 lies in neither one. Because 0 is not an end, the endpoints are not included, right? So there's no connection between 0, 1 and -1, 0. And but by -1 infinity and 0, also no connection. So that's it. And then finally, not finally, there's more. From -1, 1, let's do the -1, 1. Interval from -1 to 1. Does it have anything in common with this one? Yeah, 0. No, not 0. -1/2. Okay. And this one has something in common. Yeah, -1/2 again. Same reason. And that's the only two that I have to look at. So that takes care of this guy. And now is the question, is there a link between those two? A link, an edge? Yes, and there is. They intersect. Okay. Not very instructive, but okay. Let's do question number 33. So we have a bunch of instructions. S1, S2 is the instruction x is x plus 1. S3 is the instruction y, or assignment y is 2. S4 is, this is a 2. Z equals y. S5 is the instruction x is x plus 2. S6 is the assignment y is x plus z plus 2. This is a 2 here, sorry, my 2 and my z sometimes look a little bit the same. And then S7 is the instruction z is 4. Okay, so this is the so-called precedence graph, meaning do I need, so let's start with S1 here. Okay, do I need S1 to be able to carry out S2? Yes, I do, because, oh, there's an equal sign missing. In S2, I am using a previous value of x, so x has to be defined already, so there is definitely an arrow. These are directed graphs, right? So from S2, okay. What about S3? Now, S3 seems to be something that is, there's a defined y there, so I don't need to know what S1 was, so there's no arrow there, so S3 goes for the moment there. S4 seems to also not be involving itself with x, so I don't care about that, but S5 definitely requires me to do, well, I need S1 because it has to be defined, but in S2, x has been redefined, and I want to make, remember this program, this is a program that is supposed to be carried out in this order, and what I want to do is kind of separated in different calculations by different computers, but I have to get the same answer. So if I at some point defined x, then everywhere else I have to use that new x. So S5 has to use this new instruction. So S5 has to depend on S2. So we get here S5. But of course, and this is what we call transitivity, right? We also have to have an arrow there. You have to do also S1 first, but that's obvious because you have to first do S2 before you can do F5, and before you do S2 you have to do S1, so that makes sense. Okay, S6 is again even higher up here because it uses the latest x, so it uses what S5 has calculated, but then by transitivity we also would have S2 needs to be carried out first, and for the same reason S1 has to be carried out first. You get kind of this onion-shaped thing. What about, so I kind of took care of everything that uses somehow x in there. What about S3? Well, S3 is set with, but S4. Well, S3, we need to carry out S3 before we can do S4, because in S4 we need the value of y. And so the next dependency precedence is going to be S4 needs S6. We need to do first S4 before do S6, because we use z in there, which is defined in S4. And therefore we also knew S3 in there for the same reason. And then finally, what about F7? Now you say, oh, okay, z, it needs S4. No, in S7, z is redefined. It doesn't matter what it did before, so S7 really stands on its own. Whatever happened before, I don't care anymore, because at this point, I need 4. Okay. Good, that's the precedence graph of this particular program. It was easy. These are easy homework problems, but we will get into more interesting ones.